So today we're going to discuss a very important technique when it comes to computing both derivatives and integrals. For the next two sections we're going to concern ourselves mostly with the derivative applications, but it's going to come back and we're going to use it with integrals too. So in the past two sections we discussed the product rule and the quotient rule, and while they were helpful for derivatives, they weren't really helpful for integrals. This chain rule is going to be helpful for both. But as always, let's look at an example. Suppose I said to you, find the derivative of this function 3x plus 2 to the 20th power. Well, you'd stare at it and you'd say, well, it's not a product, it's not a quotient. I guess the only thing you could really do is you could multiply this thing out, but you're going to have to multiply 3x plus 2 times 3x plus 2 all the way down to 3x plus 2. You're going to have to do this 20 times. Not 20 factorial, just 20. Anyways, that's a lot, and you'd probably just skip this problem. It's not worth the effort. You just take your lumps, take your losses. So the problem is why is this question so bad? If I asked you instead to find the derivative of f of x equals x to the 20th, you wouldn't think it was too bad, too difficult. That's a nice power rule. If I said to find the derivative of 3x plus 2, once again, that's a nice polynomial. It's not too bad. You probably would try to do that problem. Well, why is their composition so difficult? So that's the key here, is that h of x, the function we have, is really the composition of f and g of x. This is really equal to, if we took the function g of x and we put it into the function f of x, this is what we would get and try to compute the derivative. So taking these two functions and composing them is difficult. So really, the key to this section is looking at function composition and composing functions. So if you're a bit rusty on this, you may want to go back and review function composition, because we're going to do a lot of it and you really need to be able to recognize when we compose functions. So what we have in front of us is called the chain theorem, and the chain theorem should really almost be called the composition theorem. It really helps whenever you have a composition of two or more functions. So what the theorem says is that if you have yourself one function, y equals f of u, and it's a differentiable function, it's good and you can take the derivative, and if you have another function, g, and it's a good differentiable function, and you compose them, then you can find the derivative. So up here, we have the Leibniz notation all worked out. I find it kind of confusing. What I like better is the notation down here, which says that in order to find the derivative of a composition of functions, what we do is we take the derivative of the outermost function, keep that inner function the same, and then multiply by the derivative of the outside function again. I think this is best seen with an example. So let's look again at this example we saw earlier, 3x plus 2 to the 20th. So what we have is we have an outer function here, f of u, which we can think of as u to the 20th power. We also have another function, the inside function g of x, which is equal to 3x plus 2. I know how to compute the derivatives. The derivative of this function is just going to be 20u to the 19th by the power rule, and the derivative of my inside function will just be 3. So what this means is, according to the rules, what I can do is I can write that h prime of x will equal, well, the first thing I need to do is I need to take my function. It's going to be f prime of my g of x function, and then I need to multiply this by the derivative, g prime of x. Whoops, forgot a derivative back there. Sorry about that. And so now I can simply replace. My f prime of function is 20u to the 19th, so this means this becomes 20. And inside those parentheses, that's my u, that's where I need to put g of x, which is 3x plus 2. And then when I multiply this, I multiply it by the derivative of g, which is just 3. So here I have how to find the derivative of compositions of functions. So now what I'm going to do is I'm going to take the derivative of this function again in a slightly different way. So what I think is an easier way to think about this is when I take the derivative of a composition function, what I want to do is I want to take the derivative of the outside function, leave the inside function alone, and then I need to multiply by the derivative of the inside function. And so what I end up with is 20 inside the parentheses, 3x plus 2 to the 19th. And now I take the derivative of this inside part, and I get 3. The reason I like to do it this way is because this way is going to lend itself to being a lot more useful later. But overall, I've done the exact same thing that I had before. Inside the parentheses, I still have my g of x function left alone. Outside, I've taken the derivative, and I've multiplied by the derivative. Sometimes when we look at examples, what we'll want to do is we'll want to do some rewriting first. So the thing to remember is that we can rewrite this as x squared plus 1 to the 1/2. That's all that square root symbol means. And so now when we take the derivative of y, we again use the chain rule. So the outside function we can recognize here as being the 1/2 power, whereas the inside is the x squared plus 1. So when it comes to take the derivative of something to the 1/2 is going to be 1/2, keep that inside the same, subtract 1 from the exponent. The insides just go along for the ride, and now I multiply by the derivative of the inside function. And so I end up with 1/2 to the negative 1/2. The x squared plus 1 stays in parentheses, all multiplied by 2x. So again, what you kind of want to think about is you kind of want to think about onions here. And what we're doing is we're sort of peeling away the layers. We take the derivative of this outermost layer, we leave the inside alone, and then we multiply by the derivative of that inside layer. If the onions help, think about it that way. If they don't, don't. So let's look at this function now. So this function is interesting because we actually have a composition of 3 different functions. We have a sine function on the outside. Next we have cosine. And then finally, all the way in the middle, like a little Russian nested doll, we have 2x. So how are we going to take the derivative of this? Well, there's no need to fear. This is not so bad. So taking the derivative involves just working our way through the chain rule. So the first thing we do is we take the derivative of the outermost function. The derivative of sine is cosine. And we leave that stuff that's in the middle just alone. We don't touch it yet. So we keep the cosine, and we keep the 2x there. The next step in our process is to multiply by the derivative of the inside function, which is now cosine of 2x. Because that is the next function sort of inside. Well, to compute this, once again, is not going to be so bad, because this is just going to equal this first stuff just goes along for the ride. So we have a cosine, the 2x, closing some parentheses, and then we multiply by the derivative now. So again, here we want to recognize this is another chain rule. So we'll take the derivative of the outside function. The derivative of cosine now is negative sine. We leave the inside function alone, and now we're going to multiply by the derivative of that innermost function. So it's not so bad here. We've got one more step to complete. So we have the original functions here, of course, because we've already handled taking care of these derivatives. So we just have to copy everything on down. And finally, we take the derivative of 2x, we multiply by 2. And so this is it. This is our derivative when we had a composition of 3 separate functions. So I just want to review this now. So the first step, we take the derivative of the outermost function, leave the insides the same, multiply by the derivative of the inside part. Now what we need to do is we need to compute this derivative. So to compute that derivative, what do? We take the derivative of the outermost part, leave the insides the same, multiply by the derivative of the innermost part. This innermost part has a very easy derivative. It's just going to be 2. So it's just a matter of working through this onion, peeling away the layers until we've computed all the derivatives. And this is also where the chain theorem gets its name. The idea is what we do is we just keep chaining together derivatives here, okay? So we sort of had here a first derivative, and then we chained together the second one, and we chained together the middle one again as we peeled away the layers. So let's do one more example, as long as we're in the thick of it here. So let's try to compute the derivative of this function. So if I want to compute the derivative of h with respect to my variable u, well, let's see. It's not a composition of functions to begin with. The key is to recognize is that this is really a product to start with. When we're peeling away the layers here, this product is really the layer we need to worry about when we compute the derivative. But that's not so bad. That means we just have to use the product rule. So in order to use the product rule, we take and we leave u alone, and we multiply by the derivative of the other function. So you need to multiply this by the derivative of 3u minus 9 to the 3 halves. And we'll add to this the derivative of u with respect to u is 1 times, we'll leave that function alone, the other part of our product. So the key here is to see that all we've used so far is the product theorem. We actually haven't used the chain theorem yet. But we're going to use the chain theorem when we compute this derivative. This part's done, it's just going to keep along for the ride, but we still need to compute the derivative here. And here we recognize there's an inner function, 3u minus 9, and this outer function here of something to the 3 halves. So we'll just write 3u minus 9, our inside function in blue. So now what we will need to do is this is going to equal u times, and here we're going to compute our chain rule. So the outer function, the 3 halves, comes down. We keep the inner part the same, the 3u minus 9. We subtract 1 from the exponent. And now we multiply by the derivative of 3u minus 9, which is just 3. And we have it done here. So now we can just bring the rest of this down to complete our derivative. So always working through these derivatives, it's just a matter of working through the steps. So the first step in this problem was to recognize that first we had a product rule to take care of. So the product rule, we kept the one function the same times the derivative of the other one, plus the derivative of the first function times leaving the other function the same, and then we computed using the chain rule. So then we had to use the chain rule second. So this is going to be key. Now that we know several techniques, we're going to be able to combine them all into computing derivatives. And this is an important thing now. Between the chain theorem, product theorem, quotient theorem, power theorem, trig functions, you can now compute pretty much every derivative that you want to. Not true with integrals, but for derivatives we pretty much know all the techniques there are. So here's a question that'll help you understand if you really know how the chain theorem operates. So you have two differentiable functions, f and g, and you have that h is the composition of these two functions. What do you think the derivative of h at 2 equals? Which one of these does it equal? So I encourage you to pause the video, take a chance, try to figure this out on your own. So hopefully you've waited long enough, you've given it a shot, so let's think how to do this. Well, if I want to compute h prime of something, this means I need to compute the derivative of the composition of functions over here. And by the chain rule, my composition of functions means I take the derivative of the outermost function, I leave the inside alone, and I multiply by the derivative of the outside function. So putting this all together, h prime of 2 will equal f prime of g of 2 times g prime of 2. So this means our answer is going to be number 3. That is, we can actually compute this as long as we know these quantities. Now, one of the things you may have noticed is that we went pretty quickly in the case that we had just simple functions raised to number powers. And this is called the general power theorem. As long as you have here a function raised to a number and n's a real number, then you can compute the derivative pretty quickly and easily without having to go through a lot of steps in between. So what does this mean? Suppose you wanted to compute the derivative of 3x squared plus 2 raised to the 50th. Well, you don't need to write out all functions a lot. What it is here is you recognize that n equals 50, and our inside function is simply 3x squared plus 2. So the derivative will be 50 times, keep that inside function the same, subtract 1 from the exponent, and finally multiply by the derivative of 3x squared plus 2, that is 3 times 2x. So really the general power theorem is something we saw over and over again. It's just a nice thing to keep in your mind. So here are 2 questions you should think about, and it's part of your assignment to bring to class, is you want to think, what is the relationship between g prime and f prime if g of x is equal to f of 3x? This means g prime of x equals what? Similarly, g prime of x here is equal to what? How would you go about trying to figure these things out? So we'll talk more about these in class. So the last thing to talk about is how the transcendental chain theorem works. Basically what this says is that if you have trig functions, you can totally use the chain theorem, okay? That is, if you have here the derivative with respect to x of sine of some function u, this is going to be cosine of u, that is the derivative of the outside function, keep the inside function the same, times the derivative of the inside function. And it's going to work very similarly for every single other rule that you have. The key things are secant here and cosecant. They're a little different, so we'll see an example of one of those. Suppose you wanted to compute the derivative of the secant of 3x squared plus x. Well, we know what the derivative of secant is. The thing is, though, is that it's kind of funny. It's got these 2 parts to it. It's secant tangent. So this means the derivative of the outside function is secant, keep the inside function the same, times tangent, keep that inside function the same. And now we multiply, and I ran out of room here, sorry, the derivative of 3x squared plus x. So what we have here is we have secant of 3x squared plus x times tangent of 3x squared plus x times the derivative of this will be 6x plus 1. And so that's our derivative. It's just we have to remember to keep these 2 special parts here. Let's do a couple more examples. Let's look at this function, w of t equals e to the cosine of 2t. Well, when I want to compute the derivative of this, what I need to do is I need to compute the derivative of my outside function. The problem is e to the something is just e to the something times the derivative of that something. That's what this rule says. The derivative of e to the something times the derivative. So here we have e raised to the cosine of 2t, and then we need to multiply by the derivative of that something, the cosine of 2t. Here this is neat because what do we have? Well, we're going to have another chain theorem to use. Okay, so the chain theorem here says, well, what do we need to do? We need to multiply by the derivative of the outside function, keep that inside function the same, and now multiply by the derivative of the inside function, which is just 2. So overall, this is my derivative, just using now the fact that the chain theorem also applies to these transcendental functions. As always, try the problems posted online and the problems found in this video, ask a question on Blackboard, and try the quiz. And I'll see you in class.